Let's take a look at the conical tank problem. And for this problem, the tank has a radius of 3 meters, and it also has a height of 4 meters, and I've highlighted those numbers in the diagram there in red. And this tank is being filled with water at a rate of 18 pi meters cubed per minute. And our goal is to find out how fast the water level is rising when the water reaches 2 meters deep. Okay, so we're trying to find how fast the water level is rising. So what we're really trying to find is dH by dt, so the height, how fast the height is changing with respect to time, and we want to find out when that's changing when the water is 2 meters deep, so when the height equals to 2. And we're also given the rate at which the water is entering the tank, and that's coming at 18 pi meters cubed per minute, so 18 pi, and the units are meters cubed per minute. And if I actually just line up the units with my derivative notation here, once again, the denominator is measured in time, so the denominator here is going to be dt. And since we have a cube here, that means we're measuring volume, right? So dV over dt is 18 pi meters cubed per minute. All right, so once we have all the information there, what we need to do is we need to come up with a formula that relates all of this. And when we're dealing with this inverted cone, which is a conical tank, the volume of a cone is going to be, let me write over here, volume equals to 1/3 pi r squared, and we times by the height. So that is the volume of a cone, and we'll be working with this particular formula to find what dH over dt is. Okay, so one thing that I mentioned in class is that when we're dealing with a problem like this, we know that the volume formula has an r here, right? And when we take the derivative of that expression, we should get dr over dt, right? So if I take the derivative of radius, eventually we get dr over dt. But the problem is the question doesn't give us how fast the radius is changing with respect to time. We simply just can't calculate that with the given information. So what we have to do with this particular problem is, this problem is almost designed where we need to get rid of the radius somehow, because we just don't have enough information to complete dr over dt. So yeah, this problem is designed to get rid of r, and the way we get rid of r is we create a helper equation. And what we're going to do is we're going to be using the similar triangles property here. And basically how the similar triangles property works is that we have this bigger triangle right here in red. And we know the height is 4 and the radius 3. Radius is 3. So if we write that as a ratio, the height is 4 and the radius is 3, right? So if I write this as a ratio, we know that the 4 represents the height and the radius represents 3. All right, so match the radius with the numbers, and the height is going to be 4. So I can write this cone as a radius with its height, and we can write the height and radius as a ratio right there using similar triangles. And what we're going to do now is we're going to isolate for r here, and if I do that, I can just crisscross like this. So I get 4r equals to 3h, and if I just apply a little bit more algebra here, I guess r equals to 3h divided by 4. So what this does is this tells us exactly what the radius is with respect to the height. So anytime I know the height of the cone, I can definitely calculate the radius, because the radius and height have a similar properties or relationship there. Okay, so knowing that fact now, I can now replace the radius over here. So volume equals to 1/3 pi. I can now replace the radius with 3h over 4, and then I can square that and times it by the height. And now this is looking pretty good now, because I can simplify this and find dH over dt without too many problems here. So the next step here is we want to simplify this as much as we can. So I have 1/3 pi. And if I square all this, I get 9 over 16. And then if I square the h and times with that h, I get h cubed. Right, so there you go. And then I see that this 3 and that 9 will cancel off. So now I have volume equals to 3 pi over 16, and I will times that by h cubed. All right, so here we go. Now I can take the derivative of this with respect to time. So this will be a dv over dt equals to, well, my constant is 3 pi over 16, so the constant can remain in front. And then if I take the derivative of h with respect to time, the 3 gets soccer kicked to the front, so 3h squared. And then the derivative of h will be dh over dt using the chain rule there. So we're taking the derivative with respect to time. Okay, after that, we can start plugging in the numbers here. So if I go back to the original problem here, I know that the volume is, we know that dv over dt is 18 pi, and this happens when the height is 2, so I can use those numbers and plug that into my derivative equation now. Okay, so if I do that, dv over dt, as mentioned, that becomes 18 pi. So 18 pi, and that's going to equal to 3 pi over 16. And then we have the 3 here. And remember, what's the height again? Well, the height is 2, so I can put a 2 here, and I can square that, and then I can write dh over dt. And the goal right now is to find dh over dt, right? So we're pretty much done all the derivatives. Now we need to kind of crunch the numbers out here. So I know that the pi's can cancel off, and if I multiply this number and this number, I guess I get 9, and I guess 2 times 2 is 4. So I mean, there's a lot of different ways we can kind of simplify this, so I'll try to do this in a few steps here. So 3 times 3 is going to be 9, and 2 squared is going to be 4, all over 16, and that's going to be times dh over dt. And then I guess if this 9 and that 18, I guess if I cancel that out, the 18 becomes a 2. So that becomes 2. And then this and this can cancel out, give me a 1 and a 4. So if I do 2 times 4, I guess I get 8, right? So this equals to dh over dt. So the answer is 8 here, but my units will be meters per minute. All right, so once again, meters with time, and the height here is going to be measured in meters there. Okay, so that should do it for that particular problem with the right units there. Okay, let's take a look at the next conical tank problem here. So in this problem, the conical tank has a diameter of 8 meters and a height of 10. So if I put those numbers into my my inverted cone here, I guess the height here is going to be 10. And the radius here, since the diameter is 8, the radius should be 4 here. And this is probably going to be a good hint where we probably need to use the similar triangles property later in the problem. And it's being filled with water again at a rate of 16 pi meters cubed per minute. So if I want to write the given part right now, I can, so because it's very similar to the previous problem. So this is dv by dt equals to 60 pi, and I can write the units here if I want. So meters cubed per minute, and once again, volume and volume, that measures up, time and time, that measures up as well. And I need to find the rate and change in the surface area, right? So I need to find dA. I need to find dA over dt, and I want to find out when this happens, exactly when the water surface has a radius of 2 meters. Okay, so this happens when the radius is 2 meters. Okay, so a lot of good information that's given in the problem, so you might need to take a little time to kind of organize the information on the left-hand side here. And for this particular problem, we're dealing with a few things here. So if we're looking at the water surface, the surface area of the water, right? That's this top part right here. So that's just a circle, and a circle has an area formula equal to area equals to pi r squared. But we're also dealing with an inverted cone, and an inverted cone has volume equal to 1/3 pi r squared h. And basically what we need to do is we need to find dA over dt, right? But the variable that connects everything together, or these two formulas together, is actually the radius, right? So what we need to do is I need to somehow find a way to connect these two formulas by finding the relationship between the radius of those two formulas there. So our very first step in this problem is we need to find dr by dt, and once I find dr by dt, I can find that from this particular formula, and then I want to use dr by dt to input into our area equation there to find dA over dt. Okay, so there's a lot going on in this particular problem here. So first, number one is we need to find dr by dt. Okay, in order to do that, I need to get rid of this h variable here, right? So in order to do that, we need to use the similar triangles property. Okay, so if I go back to my inverted cone here, I know that the height is 10, and I know that the radius is 4. And if I just create a ratio here like I did in my previous problem, I can match the 10 with the height, and I can match the radius with 4. Okay, so there's my ratio right there. And if I go ahead and solve for h now, I guess you really just have to make one move here. You just move the r over there, and I get 10r over 4 equals to h. And if I simplify this, 10 divided by 4 here, that's going to be 5 over 2r. Okay. All right, so let's go ahead and start connecting this all together here now. Okay, so if I rewrite my volume formula now, volume is equal to 1/3 pi r squared. Now this h will now become 5 over 2 r. So it's kind of a little bit different from the previous problem, because in the previous problem I had to get rid of r, but in this problem I need to get rid of h here. So we get rid of h using the similar triangles property there. And before we take the derivative here, let's go ahead and simplify this as much as possible here. So if I multiply the 1 and the 5, I guess that's going to be 5. And 5 times 3 is going to be, 3 times 2 is going to be 6. So 5 over 6, and then pi. And then if I multiply the radius and the radius, I get r cubed. Okay, so my volume at this stage is 5 over 6 pi r cubed. Okay, so let's erase all this, get a little bit more space here. And then from here, you should go ahead and find dv by dt. So dv by dt equals 2. All right, my constant is 5 over 6 pi, so the constant remains. And if I take the derivative of my radius with respect to time, that's going to be 3r squared times dr by dt. Okay, and we have enough information to find dr over dt, and that's exactly what we're going to do. So if I go back to my original problem here, I guess we know that using a blue marker here, my radius is 2 and my volume is 60 pi. Sorry, my dv over dt value is 60 pi. Okay, so if I plug those numbers in now, dv by dt, this becomes 60 pi, and that's going to equal to 5 over 6 pi, bracket 3, and my radius for this particular problem was going to be, going back, it's 2, right? My radius is 2, so if I plug that in here, that's 2 squared, and then I need to find dr by dt. Okay, so a little bit of math here to find dr over dt, so I guess I can cancel out the pi's. If I keep on going here, let's just write out the 60 here. I guess I get, what, 5 over 6, and this is, what, 3 times 4 times a dr over dt. Okay, and what else can we do here? I guess I can cancel out this 3, that becomes a 1, that becomes a 2, and then this 4 becomes a 2, and that becomes a 1. And then before we know it, I guess we have a 60 on the left-hand side, and on the right-hand side, if I multiply the 5, the 1, and the 2, I guess I just get 10. 10 times dr over dt. And from here, finding dr over dt isn't too bad. It's actually 60 divided by 10, which is going to be 6, right? So if I use my units, it'll be 6 meters per minute. Okay, so this is what dr over dt is. All right, so we did all that work to find dr over dt, and what we're going to do now is we need to go all the way back now. Let's go back to the front here, and we're done with the volume equation, and I'll erase all this to just create some space here. And just remember, our goal of this problem, let me just erase all, our goal of this problem is I need to find dA over dt, right? I want to figure out how fast the rate in change of the surface area at the surface of the water is changing, right? So I need to find dA over dt. So in order to find dA over dt, I just take the derivative with respect to time. So this would be dA over dt equals to pi. Pi is the constant. And then the derivative of r squared is 2r times dr over dt. And this part right here, dr over dt, this is key because we just spent some time finding that, right? So this value right here from all our previous work was actually 6. So if you go ahead and find, let me just erase all this, get more space here. So if I go ahead and look for dA over dt now, this will be pi, and then the 2, and the radius will be 2, and I guess dr over dt was going to be 6. So if I multiply all this out, 6 times 2 is 12, and 12 times 2 is 24. So this answer here would be 24 pi, and this is dA over dt. And if I look at my units here, I guess the time here is going to be in minutes, and because I'm dealing with area here, this will be meters squared. All right, so that is the answer to that particular problem.